what you're going to do, if you hit the alpha button, so that's right below the second key, and if you type in B, which is where, hopefully there, no. This really stinks that I can't see. How about this? No. Right here? That's a B? And then caret, and then X. So that's the xt theta key. All right? So I have y equals b to the x power. Now the only issue is if I graph it right now, I'm not going to see very much. And part of the reason is I don't know what b is. But if I hit second quit, I can do something like this. I can hit alpha b. No. We need that later. Let me take the number 2, for instance. And then I press this button. You guys know what this means? Store, right. Not Sports Time Ohio. Store it into alpha b. And so now, that's really the graph of 2 to the x. So if I hit the graph button now, it'll graph the function. You see that? And that is a typical exponential growth curve, 2 to the x. But I think it's worth thinking about that without the calculator, okay? Because I think you can learn some things. Let's see what this looks like. By the way, if you input 0, what do you get?
1.
2 to the 0 power. Anything to the 0 power, by the way, is what?
1.
1. That's an old rule from algebra. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is... So it really is taking off, isn't it? And this exponential growth is extremely fast. I always do this in college algebra. Oh, I don't know. Christina, I don't know if I did this with you guys. But I try to demonstrate exponential growth by playing 20 questions with a dictionary. So I give you any word in the dictionary you want, and in 20 questions I can find that word. Okay? And it's a pretty simple trick. You just say, you open the book in half. And you say, okay, is it before this page? Well, yes. Well, you just eliminated half of the possibilities. And you do it again, you do it again. And basically what you're doing is every time you ask a question like that, you're eliminating half of the possibilities. And so you've seen these little electronic versions of 20 questions. You wonder, how do they possibly get it right? It's because exponential growth is so fast that there's not even that many words in the dictionary. Really, you only need about 15 questions most of the time. Okay? So that's interesting. Now, are you allowed to put in negative numbers for x? Yeah. Matter of fact, what's 2 to the negative first power, for instance? 1/2, right? So down here is 2, negative 1 comma 1/2. Negative 2, what happens if you have 2 to the negative 2 power? Now you're at 1/4. Yeah, and what do we call that kind of behavior? That's an asymptote. So you are going to have an asymptote. Okay? You are going to have an asymptote in this type of function. And so now what you might say is, well, what happens if I change the value? I mean, that's really the next question. Tim, could you... So if I go here to, the y equals screen, and let's compare. Give me another value of the base besides 2. What do you want to see? 5. So I could go down here and do 5 to the x power. And we could compare the graphs. Well, what do you notice? It grows a lot faster. I should have expected that. It still goes through 0, 1, doesn't it? Wouldn't it be true that every function of the form b to the x power goes through 0, 1? Yeah. But I guess the next question is, what happens if I take 1/2 and put that in? Or some fraction. That's what Mike was talking about. He read that we're going to get exponential decay. And I guess I can try that. I can go to the y equals screen. I don't care about b to the x anymore. I can just do it this way. Let me take, how about 0.2 to the x power? So that's 1/5 to the x power. Enter. Graph. And actually, that might make sense to you that this would happen. Because if you think about what that looks like, when I graph 1/5 to the x power, still goes through 0, 1. If you input a 1, what do you get? 1/5 to the first power is 1/5. If you input a 2, now you're at 1/25. See, the asymptote kind of switched sides. You guys see that? If you go backwards, what's, for example, 1/5 to the negative first power? Well, that's 5, right? Because that means take reciprocal, and so you're way up here. And so that's why if you have a fraction, you're going to get exponential what? Decay. And I want to point out one more way that exponential decay is sometimes represented. Sometimes you'll see it written this way. 5 to the negative x power. If you see that, does that make sense to you guys? That that's also exponential decay? Because what's the negative exponent tell you to do? Take the reciprocal. Okay? But all of them go through 0, 1. I think that's important to understand. And I'm just going to say that from here on out, if you have y equals b to the x power, we are going to say that b is greater than 0. This addresses Matt's question. First of all, you can't take a negative number to like the 1/2 power. You can't take the square root of a negative number. We're going to avoid a lot of difficulties if we just say that, hey, b has to be bigger than 0. Like, b equals 0 would be really boring. What would that be? Well, it's just 0, right? And I guess we know that if b is between 0 and 1, then we have exponential decay. And if b is greater than 1, we have exponential growth. But again, exponential growth is so much faster than, say, a polynomial, how it grows. There's no comparison. You know, I heard some people talking about, as I walked around, some people were talking about this function, y equals x squared. Is that an exponential function? No. This is an example of a polynomial. It goes through 0, 0, 1, 1. It does go through 2, 4. But then it gets left in the dust. All right? Polynomial growth is much slower. So I think that's important to understand. Okay? So there's some basics, I guess, at least to get us started. Bless you. All right. So I said I want to talk about the derivative of this function. Okay? That's really the next thing I want to do now. Because again, this is calculus, and we want to see what we can learn. So, one last thing that we're going to avoid, because I took Jessica's graph. I thought this was kind of cool idea. She graphed an exponential function, and if you look at what it is, it's x to the x power. That's a weird function that I don't understand that well. Okay? Do you see what she's doing? It's like 1 to the first power, 2 to the second power, 3 to the third power, a half to the half power. right, we're going to stay away from that one too. But again, changing b is something I'll do a lot. But then I'm going to say that b has to be some fixed positive number. Okay? But I wanted to at least show you that because I thought it was pretty cool. All right. So what I'd like to do now is I'd like to think about the derivative. Okay? So I guess here's the question. How do I find the derivative of y equals, or let's say f of x equals b to the x power? That's my question. Do you think that bing bing is going to make much sense here?
Kind of.
Bring the x down and then put an x minus 1?
Yeah.
You think, yeah? I don't know. I mean, what would that mean? And then chain rule, then you'd have the constant. See, I get a little worried about that shortcut. If you remember when I first taught you the derivative, did I start with bing bing? Not really. How did we start it? What's the basic definition of derivative? Hey, that was on your test. There it is. What do? We know that if we want f prime of x, go ahead, Crystal. Yep. And what else do I need? We need to take the limit as h goes to 0. Okay? So we know that that's the basic definition. I can always go back to it with any new function that I get if I want to find the derivative. And I told you guys that if you want to use this formula, what you do is you fill things in. I always write down the denominator. And remember what I said I fill in next? That f of x. What is that for us? B to the x power. Is this okay? And what's this over here? Good. Everywhere there used to be an x, you're going to put an x plus h. So we have b to the x plus h power. See it? So now the next step is a little tricky. I'm going to do it for you, and then I'll see if you believe it. Let's see if this makes sense to you. I want to take that expression, b to the x plus h power, and I'm going to write it as b to the x times b to the h. Do you get that? Because normally when you multiply things in an algebra class, what do you do with the exponents? Okay, so I'm using that rule that you know kind of backwards. That's a nice trick we do in the differential equations class I teach on Tuesday, Thursday. We do this all the time. And why? Any idea why I want to do it? Yeah, Matt?
Do some multiplying by conjugate.
No, not here. Why did I rewrite it with the b to the x there? Second try, Matt? Go ahead.
Yeah, you can, if all the constants are the same, you can just look at the exponents or some sort of rule of that.
Okay. You had an idea too, Leo? And someone else said something. Was it Crystal? Do you guys see how there's a b to the x here and there's a b to the x here? Can we factor it out?
Yep.
Sure. We can factor it out front. And not only can I factor it out front, I can actually pull it past this limit symbol because this is the limit as what goes to 0. See, I'm not going to touch the x at all with this thing. So the next thing I'm going to write is that this is equal to b to the x power times, well, what are we left with? We have a limit as h approaches 0 of what?
B to the H minus 1.
B to the h is here, minus, and yes, we have to put a 1 there, all over h. All right? So far, so good?
Why,
Well, why?
why did you pull the b to the x off?
I didn't explain why.
Okay.
I just said, can I do it? And the answer is yes, I can. Right? If you distributed it back through, you'd have what we had before. I mean, you're right. Who the heck thought of doing this is a good question. Matter of fact, the next step is going to seem really weird. But I guess my question is, can I do it? B to the x power times limit as h approaches 0. And watch what I'm going to write next. B to the 0 plus h minus, and I'm going to rewrite that number 1. Isn't it true that 1 is the same as b to the 0 power? You guys get that? All over what? H. Okay. And so what this equals is b to the x times I'm going to call it a special number. I claim that's a number. And it's a special number. It's actually something that you might know what it is. What does that look like to you? Pi? Oh, not that special. I mean, when I say it's a special number, I don't know what number it is. I don't. Because I don't know. What did I never tell you? I never told you what the number b is. Are you with me? So I don't know that. But what this is, I claim, this is the derivative of f of x equals b to the x power evaluated at x equals b. No, not x equals b.
You cut.
Okay. At x equals 0. It's the derivative evaluated at x equals 0. Now, does that make sense to you guys? Right? It's f of 0 plus h minus f of 0 all over h. Okay? So let me explain one more time using a picture. This may help. All right, guys, we're going to draw a graph like this. I'm about to graph f of x equals b to the x. And so the only thing I know for sure is that it goes through what?
0, 1.
I know it goes through 0, 1. Are you with me?
Did you say that's for all exponential equations?
As long as we can pick any b we want, we see that it's going to.
It doesn't matter. Okay, so it doesn't matter if it's between 0 and 1 or greater than 1.
Right. Anything to the 0 power is 1. Right? So I'm going to draw this one like exponential growth. I know it might be decay because I don't know what b is. But I'm going to draw it like this. You guys with me? Okay. And what I'm saying is, what's the derivative of b to the x power? We worked it out and we got the answer is b to the x times a special number. You get that? And I know what the special number is on the picture. It's the slope of a tangent line. Can you draw that tangent line? Right here. Right? It's the derivative evaluated at x equals 0. So basically, the special number is this slope. Okay? Now, I thought this was applied calculus, right? This is a lot of theory going on right here. But I think it's worth looking at because it helps me to understand why we would create a very special base. Okay? In some ways, the most natural choice for your base is not 2, and it's not 3. It's actually a number in between those two bases. And no, I don't mean 2.5. I mean E. And how many people have heard of the number E before? What do you guys know about E? Anything? Go ahead. There's a formula to get it? Maybe. Yeah, I don't know what formula you're thinking of, though.
On the calculus, we had to figure out what E is.
Right. Okay. So that's kind of what I'm doing here is saying, what is E? E, by definition, I guess. Well, let me write this. How about I say this? Here's a definition. E is the special number or the special base that makes this special number equal to 1. All right? Now, you could actually figure this out with the calculator, okay? I'll show you how we would start it. I don't think I'm going to work it through all the way. But remember, we were doing some different values here. So let me go back to the y equals screen and just graph 2 to the x power. Okay? Let me graph it. And I think one thing that'll help you guys is if I zoom in. So I'm going to do that too. Because the point I'm really interested in right now is 0, 1. You guys with me? Now, I'm about to draw the tangent line there, or at least I want to compute its slope. Do you think the slope of that tangent line would be bigger than 1, smaller than 1, or equal to 1? Talk to each other about that while I get this going.
So use another special number. So the special numbers now.
Hey guys, what's the function I just graphed? 2 to the x, not e to the x. I can compute the derivative at that point, and it tells me the derivative is what, Crystal? 0.69. That's a very special number, by the way. 0.69 what?
3147.
Do you guys know that number? 0.6931. You will. You will know that number soon. Okay. So that's what happens when you put in a 2. Let's change the base. Should I make the base higher or lower? We want to make it higher so that we make it steeper so we can make that equal to 1. So if you go back here and turn this into a 3, enter, graph, and I'll be able to do the same thing. I'm going to second calculate the derivative. The derivative down here is choice 6. It tells me that the derivative at 0, 1 is, what do we have now?
1.0986.
That's too high. Are you guys with me? So it's between 2 and 3. Do you guys think it's closer to 2 or closer to 3?
3.
Why do you think it's closer to 3?
Because we're closer to 1.
Yeah, we're getting closer to 1 here. So maybe next what I should do is go here and try like 2.75 to the x power. Graph it. What do you think? Does that slope look like 1? Getting closer for sure. Here, choice 6 is derivative. And enter. It'll give me the slope. What's it say? We're close. 1.011. Up to the hundredths place, I'm okay. Then I run into problems. And that's because e is a number a little bit smaller than 2.75. Matter of fact, you can get e to the x in your calculator in the following way. Go to y equals. And let me clear this out. One way to get it, do you guys see the function that says log on the calculator? LOG? And right under it, log stands for logarithm. Right under it we have ln. Do you guys know what that stands for? Natural log. And above that it says e to the x. You guys see that? So I'm going to hit second. I'm going to hit the natural log key. So now it says e to the what? Well, I want to graph e to the x. Graph that. Okay. Looks pretty similar. Let me do this. Let me compute the derivative. So I'm going to calculate the derivative. That's choice 6. Right at 0, 1. And sure enough, it spits out, oh, well, pretty close to 1. Right? But by definition, we said that it's going to, if e is the number, see, they give me an approximate value of e in the calculator. But e is the number that would make it 1. And it's approximately 2.7 something. Actually, if you want to see what it is, here's how you could do it. Let's take e to the first power. So I'll just hit second calculate a value of 1. And it'll tell me what it's using for e. See that? 2.71, blah, blah, blah. You guys with me? So e is this very special base that we're going to use again and again. And why do I say it's special? Because, well, here's the function. Notice f of x equals e to the x is, I'm going to say, nice. Because then f prime of x equals what? Equals what?
1.
No. Let me go back to that previous slide. The previous slide said that if you start with b to the x, the derivative is always b to the x times your special number. But what's our special number going to be here? 1. So my derivative is, well, you get back b to the x, which in my case is e to the x times 1, which is what? Ha! And I want to tell you, actually, part of the reason that I'm standing here before you is because of this fact. I thought, yeah, a few homework examples would be good. Here, find the derivative of each of these. So the first one, we have x over e to the x. And then the second one, I have e to the u of x. That might look a little strange to you, so maybe I'll do the first one first. Let's see. So how do I start this problem? I want to find the derivative of this. What do you guys think I should do? Quotient rule? We could do that.
Or chain.
Ho-de hi minus hi-de ho over ho-ho, right? So let's try it. Y prime equals, what's the first thing I would write down?
E to the x.
E to the x times what?
1.
Good. Times 1, right? Ho-de hi. And then minus what? Hi is x times what?
E to the x.
Good. See, it actually works out nice. E to the x is its own derivative. All over what?
E to the x being squared.
Okay, it's e to the x being squared. I guess my question is, do you know what I can do with that?
Just equals 1.
What does it equal? How'd you get 1? Okay. What does this equal? E to the x squared. What's the rules of algebra tell me I can do with those exponents?
I just missed something.
Okay.
I thought e to the x equaled 1. That's why I was thinking 1.
E to the x? Oh, no. The special number equals 1 if that's my function. Okay? But I'll be honest with you, I'm not going to use that fact very much anymore. The fact I'm going to use now is that, what's the derivative of e to the x? E to the x. That's really the fact that I'm using, is that, you know, I wrote it here in black, but maybe I should rewrite it. The fact that I'm using over and over again is this. The derivative of e to the x is e to the x. That's maybe one of our first formulas for this chapter. All right, well, I did this, but I'd really like to simplify it. So e to the x squared, what does that mean? E to the x times, well, times 2, right? Because it's e to the x times e to the x, so you add the x's together, you get e to the 2x. The rule is that when you do a power of a power, you can multiply those exponents. You guys remember that?
Mm-hmm.
Okay. Now, you know what I'm going to do in the numerator? I'll give you a hint. It's a trick I did earlier. Gina's looking like she wants to answer, but then no.
I
Cancel the e to
can
the
say
x.
it if you really want me to.
Oh, you got it?
Yeah, you factor out the e to the x.
That's right. Because it's common here and here. 1 minus x is there. Thanks, Gina. So now what do? Well, I'd like to cancel if I can. See, once you factor things out, then you can cancel. The Mad Slasher wanted to cancel here, can't do that. You got to factor it out. And now, I guess after I cancel, I'll only have 1 minus x in the numerator, and I'll only have one of the e to the x's left in the denominator. So that would be my answer for y prime. Are you with me?
Mm-hmm.
Beautiful. Okay. The second one, it's kind of strange. I mean, you can almost think of it as a formula that I'm going to give you here. See, right now, we're doing e to the x. But very shortly, I'm going to do e to the something else. Like one of the most famous ones you get in statistics class, e to the negative x squared. How many people have taken stats? Did you guys study the bell curve? That's e to the negative x squared, all right? Well, if they want the derivative of that, or if I want the derivative of that, I need to know this idea. If I have a function, e to the something, how do I do it? Well, I get e to the something times bong. Any guesses? Does that make any sense? What rule did I just use? I used the chain rule. Because the u of x is inside of the exponential function. By the way, I don't know if any of you will do some computer programming at some point. If you ever do computer programming, they don't write it this way. They'll write f of x equals exp of u of x. That's another way to write e to the. And then it's pretty simple to see that f prime of x is exp of u of x, because we know that it's its own derivative, times u prime of x. There's actually an advantage there to doing it that way. You can kind of see that the chain rule makes a little more sense. All right. So I'm at 12:01. I think what I'd like to do for the next 5-10 minutes is give you a few exercises to work on, and then just finish the class by going over them and make sure that you understood what we learned about exponential functions today. Okay? So let me do that. Here, I have 4 problems for you to try. Okay? And then we'll put up the answers in a little bit. So we have to do e to the x quantity squared. You guys understand these are different functions, right? What's the what did you guys do to do the first one? How did you do it? What rule did you use, I guess I should ask? The chain rule?
Yeah.
Did you simplify first?
Yeah. No.
Oh, okay, so maybe I should do this one twice because some people would deal with it the way it is and some people would simplify
I
first.
think I got a really easy answer doing it without simplifying.
Okay.
I might be wrong.
Let's see what happens. And then you guys understand that the one on the right is different, okay? So, here, let's take a look. Let me go down here. So g of x, if you try to use the chain rule, you're going to get g prime of x equals bing, right? And then bing, e to the x to what power?
First.
And then bong, but what's that?
E to the
E to the x, right? So that's kind of interesting. So g prime of x could be written as 2. Now what is e to the x times e to the x?
E to the 2x.
Well, it's funny, you said e to the 2x, right? Because you're right. It's e to the x squared is e to the 2x. And I wanted to point out, I don't know if that was Matt was thinking of or not, but he said he simplified. You could-
I did it just how you did it.
You could start like this, right? Let's suppose you start like this. Then g prime of x would be, now by the way, here I'm using my u formula from above. U of x is 2x here. So I get e to the 2x back times the derivative of 2x. What's the derivative of 2x? So this is e to the 2x times 2, exactly what we got over there. Okay? 2e to the 2x. That's a couple different ways to get it. Now, what about this one, h? I think doing this one helps you really understand what's going on. Here we go. H prime of x. I know I'm going to get back e to the x squared because I know that e is its own derivative. But I also need to multiply by the derivative of what? The derivative of x squared. So you know what the answer is?
E to the x. E to the x.
E to the x squared times 2x, right?
Yeah.
And so how most people will write this answer is they'll write h prime of x equals 2x e to the x squared. 2x equal to e to the x squared. Now, I have to warn you that on the homework, I haven't posted it yet. I'm going to post it, well, by tomorrow at the latest. I thought this afternoon I'll try and get it done. But it'll be up by tomorrow at the latest. You're not just going to compute derivatives, of course. What else are you guys going to do? Well, you have to interpret, right? And so, you know, take a look at the problem. For example, here's a public health problem. Whoa, look at that function. What is that model? Suppose the number of students getting measles can be modeled like this. This is an actual, it's called a logistic growth curve, and it does model the spread of diseases. Funny thing is, it also models the spread of rumors, which is interesting. I guess you could call a rumor a disease. Matt, I was going to say something else, and then I'll take your question if that's okay.
Okay, yeah.
Okay? Hey, but all you're going to do is the same stuff you've been doing all year long. Evaluate f of 4 and interpret. I didn't have to teach anything today for you to do part A. Part B, compute the secant line slope. Well, that's AROC, the average rate of change, and interpret. Determine the limit and interpret. They didn't even have me do a derivative there. All right? We will. But I think a lot of what the homework is just kind of getting your feet wet with this stuff. So that's kind of where we're headed. Go ahead, Matt.
Yeah. Can you explain example 4?
Example 4.